Hello everyone, welcome back to BC Calculus, lesson number 25. We are talking about differential equations, and now we're going to get into some application problems where we talk about exponential growth and decay. And one of the things that I want to just say is that the differential equation dp over dt equals kp can be rewritten in terms of equation that's right here. And I just want to say that this is by population. That's what they mean by this. So population can be defined as some constant c, e to some rate, and time. And so this is what we're going to be using when we do the examples at the bottom of the page. There's a video that I posted for my AB calculus class for lesson 35, where I explain all of this to you guys. If you want to take a look at why this in turn becomes this, which you guys can see here through the process of solving this differential equation, you're going to get this equation that's right here. So let's go ahead and solve three examples. And so it goes like this. Example number 7 says the number of bacteria in a rapidly growing culture is estimated to be 10,000 at noon. All right, and then 40,000 2 hours later. How many bacteria will there be at 5 p.m.? So we're going to be given that this is our initial condition. So initially we have 10,000 bacteria. So at time equals 0, we're going to have bacteria, and again, I'm going to do 10. So B is going to represent the number of bacteria, and it's going to be represented in the thousands, all right, per thousands, because I don't want big numbers when I'm doing my problem, in thousands. And then 2 hours later, so at time equals 2, my bacteria is now at 40,000. So I'm going to go ahead and write that B is equal to 40. And it says how many bacteria will there be at time equals 5 p.m.? Well, from noon to 5, we're going to say that that is at time is equal to 5, right? So at 1 o'clock, that's time equals 1, 2 o'clock, 2, 3 o'clock, 3, etc., etc. We're looking for the number of bacteria. So that's what we want. Well, we're going to go ahead and write our function. That bacteria, the number of bacteria, is going to be equal to some constant, and I'm going to use A. I know it's up there, but we're going to use some constant A. It's going to be a rate of E to the KT. Now, what I can say to you guys really quickly is that if I'm at 10,000 bacteria, I need to find A and I need to find K, right? So that's the whole point of this. We have to find the A and the K in order to solve the problem. So E to the K, and now this is again at time equals 0. This is at time equals 0. So our initial thing is that 10 has to be equal to A, because this is simply 1, right? This is simply 1. So A is equal to 10. So I can go ahead and write that number of bacteria is going to be equal to 10 E to the KT. And so from here on out, I'm always going to make the initial value A, because it's always going to be A, because this is always going to be 1, right? When time equals 0, this is going to be 1. And so we can use now this little piece of information right here to find what K is. So when our bacteria is 40,000, then we can, and by the way, this 10 does technically represent 10,000. So I should be very careful on that. This is 10,000, but again, if this B is representing the number per thousands, then we should be good with this right there. So it's 10e to the k, and then our time is now, time has been passed 2. So 2k. And so we can go ahead and divide by 10. So we're going to get 4 is equal to e to the 2k. And sometimes some students, teachers use r here for rate, and that's totally fine. Again, these letters are interchangeable. And in order to get rid of the 2k with the e to the 2k, we have to add the natural log to both sides, right? And so we get the natural log of 4 is equal to 2k, because remember, again, the natural log of e to any power is just going to be that power, because we can move the 2k down, and this is just 1. And so k is going to be equal to the natural log of 4 divided by 2, or just 1/2 the natural log of 4. So now we can say that our equation to find any number of bacteria at any time is going to be equal to 10 e to the 1/2 natural log of 4 times t. And now this is going to give us the number of bacteria in thousands at time equals t. So this question, we want to now find the number of bacteria when we have a time of 5, right? Time of 5. So we would put this in our calculator. These are definitely calculator questions. And we get 320, which then means that this answer is going to be the number of bacteria that we're going to get at time equals 5 is going to be 320,000 bacteria. Okay. So that's the idea on how to solve these problems. So let's move on to one that's a little bit different. And this would be example number 8, where we just do a little bit of stuff, but it says carbon 14 is radioactive and decays at a rate. So basically the problem that we just did before in example number 7 was a growth, right? Bacteria is growing exponentially. As you guys can see, we started at 10,000, 2 hours later it's 40,000, 5 hours later it's at 320,000. So that growth is really going up, right? It's an exponential growth. Well, let's talk about a decay question. So carbon 14 is radioactive and decays at a rate proportional to the amount present. So we can go ahead and say that, again, we just say the change in carbon with respect to time is going to be directly proportional to the amount present. So this is, again, the differential equation that we would use to represent this problem, but we already know that C is going to be equal to A e to the kt. So you guys can always jump right to this particular problem, right? C equals A e to the kt. And really all we have to do in these problems, guys, is find the A and the K, right? So its half-life is 5,730 years. And it tells us that if 10 grams were present originally, well, that's actually really awesome for us to also write down. We know that at time equals 0, our carbon is going to be represented with 10 grams. How much will be left at time equals after 2,000 years? So we want to know what's the number. Sorry, we definitely know that. We know that at time equals 2,000, what is the number of carbon? Okay, so we're given some other piece of information that we will eventually use, all right? But the first thing that we can do here in this problem is immediately say that C is equal to 10 e to the kt, right? Because this is the initial, and this is what we just talked about in example number 7. This is our initial value. So what we can now do is that if the half-life is this, then we can now add to our list here that when time is equal to 5,730, the number of carbon is going to be equal to 5, right? That's what half-life means. It means that how many years it takes for half of it to go away. So then I can actually use this to solve for K. So we can say that 5 is equal to 10 e to the 5,730 K. It's going to be a huge number, but it's okay with this. So we're going to go ahead and divide both sides by 10, and we're going to get 1/2, which makes sense. E to the 5,730 K. And when we do this, guys, we're just going to go ahead and know that it's the natural log of 1/2. It's going to be equal to, again, the natural log of E. This would just be 5,730 K. So I skipped that one extra step. I just went and I skipped this step right here. Right? I can do that. And I like the fact that the time it took me to explain that, I could have just wrote it out and just moved on. So anyways, what is K? K is going to be equal to 1 over 5,730, the natural log of 1 over 2, or 1/2. And so that's going to be our equation that we're going to use. So C is going to be equal to 10e, this crazy number, so 1 over 5,730, natural log of 1/2, times t. And that's how we get this value of K. So we said, okay, the half-life, well, then that's going to be 5 grams. And then we're going to plug in C. We're going to plug in 2,000, right? 2,000 into our function here. And by the way, I just moved the t up here, right? So this t right here, so let's put it right there. And then with our calculator, we can be able to calculate this. Now, before we calculate it, we know that the answer has got to be, because it's in 2000, right? It's 2000 years. So we know it's got to be greater than 5 and less than 10, because it's not half its life yet. So our number should be somewhere between 10 and 5 if we did the question right. So if you plug this all into your graphing calculator, you're going to get 7.851 grams. Okay. So again, this is an exponential decay because we're losing the amount as time goes on. Okay. So those are 2 of our examples. And the last one I want to do is just another little easy puppy one. It's just a cute little puppy example where it's, again, example number 7, where it says a puppy weighs 2 pounds at birth. So we can just say that the weight is equal to our AE to the KT. And so we can immediately say that 2 is going to be our A. And then it's, when time is equal to 2, so when time is equal to 2, so we're going to do this one pretty quickly, then we know that it's going to end up, the weight's going to end up being 3.5 pounds. So we can go ahead and divide by 2, right? So we can get 3.5 over 2 equals e to the k, 2k. We know that the natural log of 3.5 over 2 is equal to 2k. And so we know that k equals 1/2 the natural log of 3.5 over 2. And so now that everything's said and done, we have our equation of W equals 2e to the 1/2 natural log of 3.5 divided by 2 times t. And then all we have to do here, ladies and gentlemen, is plug in 3 for t. And we're going to plug this into our awesome little calculator, and we're going to get that this answer is 4.6 pounds. All right, so there we go. There's our applications for our differential equations, and we're going to come back in the next video and talk about our good old friend slope fields. So I'll see you guys in the next video.